Good morning, everybody. I'm excited to be here with you on the Diabetes Canada online convention. My name's Dr. Tom Elliott. I'm a Vancouver diabetes specialist. I'm the medical director of BC Diabetes, a diabetes centre in Vancouver. And for the next 20 minutes or so, I'm going to be talking about research for a cure without gadgets. Now, everything that I'm talking about today is available through the URL on your screen, bit.ly/thecure2020. So don't worry about missing anything. I'm going to be talking about the cure without gadgets because the cure is already here with gadgets. And when I talk about gadgets, I'm talking about closed loop insulin pump and CGM systems. On this screen, you can see Savelli and Sophia, father and daughter. They're both looping, and also Rhoda Spalding. They consider themselves to be cured. They're still taking insulin, but the closed loop system is doing all the work. All they do is change their sensor every 10 days, top up their pump every 3 days, and charge their iPhone and their Riley Link every night. Ian McCullough's a little different. He's cured. He got cured with a pancreatic transplant about 8 years ago. So the cure is already here for some people, but for most of us, it's not yet here, although we do have closed loop systems. There are 3 of them available. The one with the best results is called Loop. It's a do-it-yourself system that you need an Omnipod pump, a Dexcom G6, a Riley Link, and software, and you need someone to help you. I'm willing to help, and so are others around the country. If you're not willing to do it yourself, then there are 2 retail options that are also very good. Not quite as good in terms of the sugar control, but they're improving every day. The Medtronic 670G pump and the Tandem T-Slim X2. Both of these will be full closed loop systems soon. So the plan today for my talk about the cure without gadgets is to talk about transplantation first. Transplantation by definition is a late intervention. People who get transplants have already had diabetes typically for a long time. We're going to talk about pancreas transplantation, which was how my patient Ian McCullough was cured. By the way, I should add, I saw all 4 of those people in the last week. And then we're going to talk about cell-based transplantation, either with human islets or with human islets that are grown up from human stem cells. And then at the end, we're going to talk about another cure, that's prevention. My mum told me that an ounce of prevention is worth a pound of cure. And that's ultimately how I got involved with this talk today, because I'm involved in a number of prevention studies. Well, pancreas transplantation is exciting because it does lead to a cure. People who get pancreas transplants are at end-stage renal disease, meaning that they either already have a kidney transplant in place or they're about to get one. So people who get pancreas transplants typically get it at the same time as they're getting their kidney, or occasionally after they've had a kidney and everything's working well. The kidney and the pancreas come from cadaver donors. These are people typically who've been killed in road wrecks and who've kindly offered to give their organs for transplantation. The pancreas does 2 things. It makes digestive juices, and obviously we don't need digestive. People with type 1 diabetes typically have no problem with their digestive juices. So the pancreas is sewn in to the top of the bladder so that the digestive juices go into the urine, and people with pancreas transplants have cloudy urine from the pancreatic juice. But the vascular system, which is what gets the insulin from the endocrine pancreas, is sewn into one of the mesenteric arteries. So that's how people get their insulin from the pancreatic transplant. About 100 of these are done in Canada per year. All provinces except Saskatchewan and Manitoba have a program. And as I mentioned, you won't get a pancreas transplant unless you're about to get a kidney transplant or you've already got one. So that means you've got end-stage renal disease, usually from diabetes. It does require immunosuppressive therapy. So if the immunosuppressive therapy is stopped, the kidney will fail, and so will the pancreas. Immunosuppressive therapy is life-saving, but it is not without problems. There's a slight increase in risk of cancer and infection in people taking immunosuppressive therapy. So it's not something you get into without some thought. The results of pancreas transplants are very good. More than 90% of pancreases are still working 5 years afterwards. They're even better than kidney transplants, which are otherwise the safest organ transplant available. Now we're going to talk about cell-based strategies to treat type 1 diabetes. So people have type 1 diabetes because they've run out of beta cells. When at birth, there are roughly 10 billion beta cells in 10 million islets within the endocrine pancreas. So we can transplant working, and those 10 billion cells have been killed off by the immune system. We're going to talk at the end later about how we can turn off or dampen down the immune system destruction of beta cells. But if you've got type 1 diabetes and you've had it for more than a year, then you're down to less than 5% of your 10 billion cells. So if we were going to do a transplant, we could get islets and beta cells from a cadaver in just the same way that a pancreas was taken, or we could get it from other animals, including pigs. This is not part of the human transplant program yet. Or very interestingly, and now the main focus of islet cell transplantation is making these islets from pluri-potential stem cells. Embryos are something that we can be used in the Western world. Embryos are not used for this type of research, but we grab these cells from fibroblasts, which are in the skin, and we grow them up. And we get islets just as we would get from a human pancreas donor or from a pig. And then we transplant these islets into the human body. And inside the human body, we hope that these islets make insulin, and switch insulin on and switch insulin off, so you don't go high and you don't go low, you just have perfect control. So that is what I'm going to be talking about for the next 10 minutes. That's cell-based strategies for type 1 diabetes, islet cell transplantation. Well, islet cell transplantation from human cadaveric donors has been studied extensively in the last 20 years. Indeed, it all started out in Edmonton, and the protocol used in most centers is actually called the Edmonton protocol. The islets come from cadaveric donors, so the pancreas that you saw in that earlier slide, which was sewn into the bladder, is mushed up, and with a lengthy extraction, the islets are available to be infused into either the liver, which is what is typically done, or sometimes into the spleen, or sometimes put under the kidney capsule. Islet cell transplants, just like pancreas and kidney transplants, require immunosuppressive therapy. So people on islet cell transplantation from human donors need to take immunosuppressive therapy with the caveats that I've spoken to about increased risk of infection and of certain cancers. The problem with human islet cell transplantation is that the graft survival is low. Fewer than 20% of people who get one of these transplants are still insulin dependent at 2 years. At 1 year, it's less than 50% of people. So the first problem is that the islet cells die off for reasons that are not well understood. The second problem, of course, is that there aren't enough pancreases available. Those pancreases, you remember, have to come from road wrecks. So that's islet cell transplantation. There's not much happening out there for those two reasons. What is very exciting now are islets that are coming from stem cells. So stem cell transplantation is where most of us in the biz and involved in the science are very excited. So the first thing that needs to happen is that we need to isolate a pluri-potential, isolate cells, and typically these are skin fibroblasts. We grow them up in a petri dish in a lab. Then we treat these cells with factors that reprogram them and make them turn into pluri-potential stem cells. These are stem cells that can turn into anything. Now, you all know that each one of us started out as one cell. Our mother's egg and our father's sperm joined, and that's the ultimate pluri-potential stem cell. It becomes a human being. Well, we can grow these pluri-potential stem cells in the lab, and we can make them turn into blood cells. We can make them turn into gut cells. We can make them turn into muscle, and we can make them turn into islets of Langerhans, which contain beta cells, and beta cells are what makes insulin. So that is the excitement about stem cell transplantation. Here's another cartoon that has two parts to it. In the top part talks about humus pancreatic development. That takes 9 months. That's when we're in our mother's womb. And that wonderful initial cell grows up to make a full pancreas. Well, we can mimic the same system and do it in around 5 weeks in the laboratory by applying various factors to cause the cells to differentiate and to grow. So that is the technology that is behind stem cell transplantation. There are a number of companies out there working on these programs, and this is where our interest lies now in terms of a hope for a cure for those of you who've had diabetes for a long time. So once we've grown up the islets into millions and billions, here they are shown in the middle of this capsule, we then need to put them inside a capsule, and this capsule has to have several features. We would like it to be impervious to immune cells. So we would like it so that when we transplant, we put this capsule into the human body, that doesn't get killed off by the same process that caused type 1 diabetes in the first place. We need it to get oxygen and nutrients so that it can grow, so it needs to have a good blood supply. And then we need it to be able to release the product of interest. And of course, in the context of diabetes, we want the transplant to release insulin. We want insulin to be switched on and switched off, just like our islets before they got destroyed by the immune system. Here's a photograph of skin that was taken from a laboratory animal, where you can see one of these capsules containing islet cells grew up very successfully. And you can see the blood supply that was providing the nutrients. And I can tell you, in these laboratory animals, these transplants were making insulin. And here's a closer view showing the blood supply that's so important for survival. The company with the most advanced research today is called ViaCyte. And ViaCyte has been working on these encapsulated stem cell transplants now since 2014. A phase 2 study has just been completed. Phase 2 is all about safety, making sure that no one's going to get hurt by it, and efficacy. Does it work? The phase 2 study is about to report. At the time of this recording, it's about 2 weeks prior to when it's going to be released. So I can't tell you the results of the study, but I can tell you that the results are very promising. The ViaCyte transplant requires immunosuppressive therapy. So remember on that previous slide I showed you the cartoon hoping that we could prevent the immune system from attacking the capsule. Well, currently we haven't figured that out, but that's one of the next obstacles that will be circumvented. So patients getting these transplants need to be on the same immunosuppressive drugs, the tacrolimus and mycophenolate. They get a general anesthetic, and 5 or 6 of these capsules are implanted into their abdomen through each one through a 4-centimeter incision. So if you were to look at somebody in a bathing suit, you might see the tiny scars from the incision. You wouldn't see a bump from the capsules. Even though I can't give you the results because I haven't seen them, I do know, a little birdie told me that these capsules are producing insulin, and a number of patients who've received them have been able to reduce their dose of insulin very significantly. Now, the next set of studies that are starting up individuals will be given 3 times the number of islets. So the potential to make insulin will be tripled. The study's open label, meaning that nobody gets placebo, everybody gets the active therapy. And these studies are recruiting. So if you're interested in participating, listen up. You need to have type 1 diabetes. You need to be compliant. That means that you can't be in and out of hospital. You can't be passing out with low sugars. You can't be getting DKA. You have to have a decent A1C, a decent time in range from your CGM. You have to have some hypoglycemia unawareness, but just about everybody has that if they've had diabetes more than 10 years. There are 2 sites in Canada, one in Vancouver and the other in Edmonton. The principal investigator in Vancouver is my colleague, Dr. David Thompson, and he would welcome you sending him an email if you're interested in participating. Well, the last part of my study is about prevention, and that's indeed why I was chosen to give this talk, because I've been involved in a number of these studies over the years. As mentioned, we all start with 10 billion cells, and we get type 1 diabetes when we're down to our last billion. All those cells have been destroyed by the immune system. The question is, what if we could stop this destruction while we still had enough cells to control sugar? And what if we could actually help those cells regenerate? That's where the interest is in prevention. Here's a cartoon that takes us through a thought experiment. Imagine if we found someone who had autoimmune destruction of their beta cells, but we got to them way before anything happened. So here's somebody with 100%, so they've still got their 10 billion beta cells. The autoimmunity has begun. We can record that by measuring autoantibodies in the blood. Blood sugar hasn't been affected. There's no symptoms because they still make tons of insulin. Maybe we could intervene at an early stage with a drug that stops the destruction. If we could do it very early on, then we'd be very confident about getting good results. And in fact, we've already shown that we've got great results if we get people early enough. Typically, we find people when they've got fewer than 50% of their beta cells left. If we give them a glucose-rich meal and measure their sugars 2 hours later, it's high. So it shows that they can't make enough insulin, but they still don't have symptoms. Here's another point at which we could intervene. And then finally, typically we only get to see people once they become symptomatic, once they've got thirsty, they're losing weight, their sugar's sky high, and they're diagnosed with type 1 diabetes. At that point, they generally have, let's say, somewhere between 10 and 20% of their beta cells left. And this has been the focus in the last 15 years of research programs using different drugs. And this study shows intervention at late stages and then progressively earlier stages, each different intervention with a higher likelihood of success the earlier we intervene. Here's a cartoon showing just how complex the immune process that leads to type 1 diabetes is. It's way above my pay grade, but there are very clever immunologists who design studies using monoclonal antibodies which block the destruction of beta cells at various points. Interleukin 12 is another, interleukin 23 is another one. And then there are various cellular factors that can also be used. So these are all points at which we can intervene to prevent the development of type 1 diabetes. I've been involved in these studies now for 12 years. The first study I was in was in 2008 with DEFEND-2, and Savelli, the father in that picture earlier on, was involved in that study. 12 years later, he obviously wasn't cured by being in the study, but he's now got his closed loop system and he considers himself cured. In 2016, I was involved in a study with ustekinumab, which was open label and showed some excellent improved beta cell function. We had one patient who was in a honeymoon for 2 years. And because of that, next month we are starting a phase 3 study, phase 2, phase 3 study, a randomized controlled trial using the same drug. So this is for people with newly newly diagnosed diabetes within the first 100 days. I was involved in Extend, which is just about to report. And then I'm involved in Protect, which is a study in children using the drug teplizumab. And interestingly, as I'm doing this recording, we have our third patient being randomized into the study. So in summary, to get a cure in 2020, you need to either have end-stage renal disease and to either have a kidney transplant or to need a kidney transplant. And that option there is to get a pancreas somewhere from a patient in a road wreck. Otherwise, apart from closed loop pumps, the only option really are for stem cell transplantations. And we look forward to developments with ViaCyte and other companies investigating encapsulated stem cell transplants of islet cells. I think my time's up, and now I'm ready to take your questions.